أحب أبدأ المحاضرة بأي ملاحظات عندكم على الاختبار، على النظام بتاعه أو على أي مشاكل قابلتوها في أثناء الاختبار. If you have any problems about the exam, the midterm exam, just let me know please now.
بخصوص بس الترو والفولس والمالتيبل تشويس، كان في أشياء كثيرة يعني صعب إن تلاقيها مثلا في سلايدز، يعني شرح مثلا.
We're gonna go over them now and make sure that I'll let you know exactly where they are. Okay, don't worry about that. What else?
زي question 3 في هذه كمان ما عرفت أنا من فين.
I'm gonna go over all the questions. I'm talking about the way the exam was handled through Blackboard. So basically,
it was handled good.
Did you have any comments? Did you have any problems with any particular aspect? Did you have any problem with Blackboard or while uploading your file, anything like that?
No,
it's perfect.
Were you able to retrieve the graded version of your exam?
Yes.
But except the answers for the true and false.
You are on the system now. Whenever you go into the basically your trial, you're gonna see all the questions and you're gonna see the what you submitted and the true solution for each one. So you can see that through Blackboard. Okay, so what I will do first is just go over the problems in the exam and basically try to give you the idea behind each one of them. Some of them were particularly, I'm not sure, not many of you solved, for example, the first problem. Okay, let me go over the first problem and just give you an idea about what you should do there. What you have here is, what you're given here is the electrical power rating. This is electrical. Okay. Basically, when you're buying an electrical appliance, the rating, the power rating for the device, the power rating that is written on the device is not the mechanical rating, it's the electrical rating. It's basically what you're going to withdraw from the AC mains, for example, okay? So basically, this is electrical power rating. This is not the mechanical power rating. You have an efficiency of 80%. So basically, this means that this electrical power rating basically will be converted to mechanical through this equation here. Okay, so this means that the mechanical power should be 16 watts. Okay, you're given here the speed basically, okay? And you know that the power, the mechanical power is equal to M times omega, okay? And basically you have the mechanical power from here, and you have omega from there. Okay, so you'll get from here, you get M. This is the first requirement. Basically, this is the torque that you would like to have. The thing is, you have a motor, and this motor gets 20 watts, and basically outputs mechanical energy of mechanical power of 16 watts. Okay, basically, you're getting this 20 watts. If you look at this here, you have a 24 volt DC. So basically get this as 24 volt DC input, okay? You have an adapter, okay, that gets the 220. This is just like the adapter used to charge your phone or something like that, okay? You get 220 AC, okay? And you convert it to 24 volt DC. But actually, there is an efficiency here of 0.9, meaning that whatever power you have here, this is the power input, the AC power input, okay, will be multiplied by 0.9 to get this 20 watts, okay? So the power input should be equal to 20 watts over 0.9, okay? So this will give you the power input. What I'm asking here the part C here is the electrical energy. And I told you that basically this motor was running for 1 hour. So when you get this power input, you get the energy input as P input times 3600, which is 60 by 60, in order for you to get the energy by joule, in joules. Okay, so most people basically got confused what these efficiencies are for. If you read the problem carefully, you will know exactly what each one is for. The efficiency of the motor means that the efficiency of converting the electrical energy input into mechanical energy output. And you have very clearly here, the energy here is very clearly electrical, it's not mechanical. Okay, for example, when I buy a kettle, for example, did you get the heat energy output of the kettle? The rating of the kettle is the heat energy output. It's not the heat energy output, it's the mechanical, it's the electrical energy input. So basically, you should multiply that by 0.8 to get the mechanical energy, and then you use that to get the torque that you need here. Okay, the power input, the AC power input, is basically supplied through an adapter that converts the 220 AC to 24 volt DC. And the efficiency of this conversion is 0.9. So basically the power you have here, this 20 here, is after this 0.9 efficiency. So the actual power input is 20 over 0.9. It's going to be more than 20. And if you multiply by 60 by 60, because it's 1 hour, you'll get the energy. Okay? Do you have any questions about this?
No.
By the way, the solution I'm writing right now, I'm going to post it like it is right now on Blackboard, so that you will have the solutions for the midterm exam. Okay? I think this problem was straightforward. So yeah, I think more than maybe 70% of you made that solution correctly, but there was an error here, one common mistake here, in that basically we said that the delta I maximum basically should be delta R partial I partial R absolute value plus delta V partial I partial V partial I partial V, sorry, absolute value. Okay, basically from here, this is 1K and this is 1%, meaning that delta R is equal to what? 1000 times 1%, this is equal to 10. Okay, and partial R, partial I partial R is equal to what? You have basically the main equation basically is I is equal to V over R, right? This is the main equation here. Okay, how much is that? If you want to get the derivative with respect to R, it's going to be minus V
over R squared.
R squared.
Negative V over R squared. But
which is equal to what? V is what? V here is 10, okay, over R squared, 10 to the power 6, right? Minus 10 to the minus 5. And you have delta I, delta V is equal to, many of you made this mistake, the voltmeter accuracy is 2% of its full scale accuracy. Full scale. It's not related to the voltage itself. So basically it's 2% multiplied by 25, not 10. So it's going to be what?
0.
2 times 25 is going to be 0.5. It's not going to be 0.2. Okay? And partial I, partial V is going to be equal to 1 over R, which is 10 to the minus 3, right? The nominal value for I from here will be what? V over R, 10 over 1000. So it's going to be like 10 to the minus 2 amperes. This is the nominal value. All you have to do is just substitute everything here in this equation. You will get that delta I maximum is equal to delta R. Delta R is 0.5, is 10 times partial R, partial I, partial R, which is supposed to be minus 10 to the minus 5. You have to make sure that you put it minus 10 to the minus 5. That's it. You don't put any negative sign here because you have the absolute value here. Many of you actually put the negative value and computed the result with the negative value, and this was incorrect. And if you add that also, this is 0.5 times 10 to the minus 3. So this will be equal to what? This is like 0.1 times this. It's going to be 0.6 times 10 to the minus 3, right? And if you divide that by 10 to the minus 2, you find that it's what? You end up having basically delta I max over I equal to 6%. So just make sure that you have the absolute value here. This is very important. Okay. Make sure that you use the full scale range here, not the actual voltage. And that's it. This is just regular, like many of the problems we solved in that particular part. It's not, it doesn't have any new idea or anything like that. It's just direct application of the regulation of the rule here. Just apply the formula as is. Anyone has any problems with that?
No.
Any questions? Okay, so we'll move on. In this question here, I'm asking you that this is the input signal, this is how it looks like, and a student made it, or basically the setting of a particular student was like this, made the output look like this, and the other student made it look like this. If you look at the same point, the point that you started with, they are both basically started at 0. So basically the trigger level is 0. So basically here it's a problem related to the trigger because this is the starting point. Because the starting point was different. But actually the trigger level is the same. So basically it's definitely not the level. The slope is the one that is different. Here you have a positive slope because actually what you have here is 0 going up. And here it's 0 going down. So basically it's just the difference between the slope. Here it's a positive slope and here it's a negative slope. That's it. This question was answered correctly by almost half the students. It's not related to the time base, it's not related to the voltage scale, it's not related to anything but the trigger, because basically the signal itself looks at the same, basically it has the same time scale, because basically if you look at a similar part like this part, for example, look at it here and there, it looks the same, it has the same number of units here. And the voltage scale is also the same. So basically the length here is exactly the same as the length here, it's not different. So it's not related to any of them. It's related to how you started the writing or drawing the waveform. And this is definitely related to the trigger. Some people actually mentioned the trigger, but didn't mention the slope. So basically, so the slope here is the answer. Okay? If you just mention the trigger, you got only half the points, basically. You got like 4 or something like that, 4 out of 12. Okay? But actually, what you have, actually, the points here are different, by the way. It wasn't, it was like 8. So basically, if you just mention the trigger, you got 4 out of 8. If you mention the slope, you got 8 out of 8. Okay? Any questions? So moving on. Here it was very simple. Most of you actually did this correctly, like 80% of the students. All you have to do is, I'm not asking you to compute the shunt resistance or the series resistance. I'm asking you for the opposite. I'm asking you for the range. So what you're going to do here is just write the equation. For example, for the voltmeter, you have the V scale or maximum is equal to I full scale deflection times RS plus RM, or moving coil, okay? Basically, you have this, you have this, you have this, you compute P maximum. It's going to be like 10 volts. And the other one here, for the ammeter, you have I full scale deflection times R moving coil is equal to I full scale deflection minus I moving, minus I, basically here it's I maximum, or the range basically, minus, or IT, it's fine, I full scale deflection times basically R shunt. You have this, you have this, you have this and this, you need this. It's going to be like 1 ampere. Any questions? You have any questions about this? Okay, we'll move on. Here we have a problem of loading, and several of you actually, for some reason, were probably, because all the problems we had like 10K and 10K resistors. So we have here a source, and we have here our source, and we have our load, okay? And basically you put here the voltmeter, and basically voltmeter has RV. And what you need to have first, compute first the reading on the voltmeter. Some people actually made mistakes in computing the voltmeter resistance. It should be RV 20 kilo ohms times the range. The range actually is very clearly written here as 50, so it's going to be like 1 mega ohms. Okay. When you have here RL equal to 10K, and this is 100K, it's not 10K, because usually all the problems that you saw probably in the homework had here RS equal to 10K. Here you have 10K, and this is 100K, and this is 1 mega now. So all you have to do is just compute the parallel combination of these two. It's going to be around 9900 volts. And based on that, you compute the actual reading, the measured, V measured, which is going to be equal to 9900, or let me write it down as, it's fine, 9900 over 9900 plus 100K. It's not 100, it's 100K. Some people actually put it like 100 only. They didn't put it like 100 times 10 to the power 3. So that was a mistake. And you will get that. V true is equal to 10K over 10K plus 100K. You will get that. And after that, you compute the loading error. Percentage is equal to V measured minus V true over V true times 100%. This is going to be like, if you compute it accurately, you come up with like 9%, minus 9%. Minus is very important, okay? Just remember that minus is really important, okay? Minus is as important as the 9, okay? If you do it without any approximations for the values, you get like minus 9%. But if you get it with some approximation, if you approximate it here, or there, you will end up with like
it's 0.9.
0.9, right? That's right. That's right. So basically, it's just 0.9%, minus 0.9%. Yes. Basically, it can be like 0.8 minus 0.82, something like that. If you have any approximations here or there, make sure that when you approximate properly. Basically, if you have 1.0909, it's approximated to 1.091. Okay, this will make a difference. Okay, because actually you cannot approximate 0920. Okay.
But the first 3 digits.
What do
It's
you mean
okay.
the first? What do you mean the first 3? It's fine. Yeah, if you write like this, it's going to be very close. Yes. The same thing for the other one. If you have 0.08, the other one I think is going to be like this. I'm not sure which one is which, but it's like it's going to be something like this also. So basically, you have to approximate this also to 1. Okay. So just make sure that you don't round the 0, don't round the 9 to 0, because basically it's not right to do it like this. You have a lot of difference. You have a big difference actually if you do it like this, because the differences are very small. When you approximate like this, you will have an error added to your result. Any questions? Okay. Again, the solution I'm writing right now actually is going to be on Blackboard. So don't worry about it. You don't have to write down the solution that I'm writing, okay? You don't have to do that. Here we have an analog ammeter based on a moving coil instrument. This problem actually we solved exactly the same problem, or a very similar problem actually in the review lecture. Basically, the full scale deflection current will be equal to 9 volts over 10K. Because basically, you are assuming that you have a resistance, the resistance you're measuring is 0. So you'll have that. This is corresponding to a full-scale deflection of 120 degrees. The current for 100K will be equal to 9 over 10 plus 100. So you'll have that, okay? This is corresponding to the angle that you want to have. So basically, basically the ratio between these two is equal to the ratio between these two. So you get your angle as 10.9 degrees, around something like that. You have any questions? This was a very simple problem, actually. Okay, let's move on to the true-false questions. The first one, the oscilloscope mode that displays a waveform only when the trigger conditions are met is called, it's supposed to be normal. This is one of the things that we said in the lecture, actually. In that particular lecture, it was one of the things that I emphasized, actually. The difference between normal and auto. For the single, you do that only once, okay? But here, I didn't mention that you're going to do that once, okay? So whenever you have a trigger condition, you will display the waveform. So this is a normal. This has nothing to do with external trigger. External trigger doesn't work like this. External trigger is basically, this is a source of trigger. This is not the mode of trigger. And the auto actually forces trigger whenever you don't have trigger. So basically, if it waits for a particular period of time without trigger, it's going to force triggering. So basically, it's going to display something that doesn't have a trigger. Okay. The deflection of the dynamometer-based AC ammeter is proportional to, we know that in this particular case, the deflection angle will be proportional to B times I, okay, times the other parameters, of course, okay, times the area and all these things. And B basically in the dynamometer is basically alpha times I. So it's a constant times I. So basically you end up having your theta dependent on I squared. And as you see, as we said before, basically the deflection, the actual deflection, the steady state of the actual deflection would be proportional to the average of that, because it's an AC waveform. So the average of the square will be basically what you have here for the deflection of the dynamometer-based AC ammeter. Here it should be very clear, actually. The oscilloscope circuit that controls the stability of the trace. Stability meaning that the trace comes always, you start from the same point and go through the same exact curve each time, so to see a stable trace on the scope itself. If I start each time from a different place, so basically this means that sometimes I start like this, sometimes I start like this, sometimes I start like this, sometimes I start like this. So basically I will see different things on the scope. So basically this is related to the trigger. It doesn't have anything to do with the amplifier, doesn't have to do anything to do with the time base. It has everything to do with the trigger part. To minimize the loading effect while measuring voltage, we should use voltmeter with largest instrument resistance, oscilloscope with the smallest instrument resistance, dynamometer, rectifier voltmeter. Both of these actually, they are exactly the same as the other ones here. They are not any different, but basically these are AC instruments, okay? They are not really gonna do anything different from the other ones here. But here, what you need to do, if you remember from the problem that we were just solving, the problem here, if this voltmeter here had an infinite resistance, if it has a very large resistance that approximates infinity, then the parallel combination between these two here will be just the RL, meaning that the error will be very small. So basically, when you have a voltmeter with a very large resistance, it will basically be closer to the ideal situation of having basically an ideal voltmeter that does not affect the circuit. We have to also remember, like what we did in the lab, if you use an oscilloscope to measure the voltage, then it acts like a voltmeter. So the resistance of the input resistance of the oscilloscope would be basically as if it was the input resistance of the voltmeter. So when I have an oscilloscope with a very small instrument resistance, this means that it's going to affect your circuit incredibly, basically it's going to have a large effect on your resistance, on your load resistance, because basically you will have the load resistance in parallel with very small resistance from the oscilloscope, which means that it's going to affect the combination. It will be very different from just the load resistance. So basically this is definitely wrong. So basically this is the correct solution. Here, what we have here for the dynamometer AC ammeter, basically it's very close to the solution of this part here, okay? The deflection is proportional to I square, basically, okay? It's proportional to I square. This means that, as I told you, this was part of the lecture, actually the revision lecture, when we said that the distance from 0 to 1 is gonna be basically much smaller than the distance from 1 to 2. So basically this will be 1, this will be 4, because basically the deflection is proportional, not the value of the current, no, the square of the value of the current. Okay, so what I'm looking for here is a scale that is not uniform. This is uniform, this is incorrect. This is basically opposite. Basically it has 0 to infinity. It cannot be an ammeter, basically, definitely. You cannot have infinity in an ammeter, okay? Here you have a nonlinear scale, but actually the distance for one is much larger than the distance between any other ones here. So basically this is not proportional to the number square. This is not proportional to I square. So this is incorrect. This is the closest thing to the correct value, because actually the distance here is smaller than the distance here, okay? So basically see here the 1, from 0 to 1, this is actually larger here, this is larger here, this is larger here, so on. So basically, see here, the 2 here, the distance between 8 and 10 is much larger than the distance from 0 to 2 here. So basically, this should be the correct one. For the true-false, the electron gun in the cathode ray tube allows moving the trace anywhere on the screen. Basically, the electron gun, the function of the electron gun is just to generate the beam. That's it. It doesn't move it anywhere. So this is incorrect. The control grid voltage controls the focus of the trace in the cathode ray tube. The control grid actually controls the beam, the intensity of the beam. It doesn't control the focus. So this is also fair. Yes.
For example, these questions, I couldn't find it in the slides. The electron gun in cathode.
Actually, basically, the slides are coming from the textbook. I explained that. I cannot have all the explanations in the slides as text. So basically, I explained everything in the lecture and told you basically that everything, whenever somebody asked me about the details, I told them to just go to read the 3 pages that are written about this in the textbook. Okay, if you look at the slides of the oscilloscope part, you will find that basically it has figures, and I'm explaining everything on the figures. So you have to go back and look at the textbook and basically read the whatever I was saying in the lecture. You will find it in the textbook. It's only like 3 pages. It's not like a chapter or something like that. It's just a few pages. You just basically say exactly what I was saying in the lecture. So basically, the control grid function it controls the intensity, not the focus. Gross errors can be different when repeating a measurement using the same methodology. This is one of the things actually we actually talked about in the revision lecture. Somebody asked about the gross errors and we explained it again. We said that the gross errors are human errors. So basically it's like, for example, if you are solving a mathematical problem, a numerical problem, a multiplication, for example, you can solve this multiplication problem. You know exactly the same method. You use the same method for the multiplication, but sometimes you make an error. Okay, so basically it's exactly the same here. Gross errors can be different because sometimes you make a mistake, sometimes you do it right. So basically this is correct. Here, the dynamometer device includes a permanent magnet in its design. This is incorrect because what we said in the beginning of the dynamometer part is that we are going to replace the permanent magnet with basically an electromagnet. Okay, this is the only difference between the dynamometer device and the moving coil, the basic moving coil that we use for the DC instruments. So basically, it does not have a permanent magnet. Here, the time-based generator in oscilloscope moves the trace in the horizontal direction. The time-based generator is basically what is applied. This is the waveform that is applied in the X deflection plates. And basically, this is actually what moves the horizontal, the plane, the trace in the horizontal direction. So this is correct. For the multi-range voltmeter, use break before make. This is correct because what you want to have there is an open circuit rather than a short circuit. So basically, you don't want to have a small RS. If you have break before make, then you have infinity in between settings. If I'm moving from this resistance to this resistance, it means that between them I'm at open circuit. And this is okay if it's a series resistance, because in this case, the current passing through the moving coil will be less than any of the resistors, which is what we want. If we have both of them connected together, if we use the other type of switch, like make before break, it means that I'm going to have a parallel combination of 2 resistors, which are going to be smaller than any one of them, and this causes the current to be higher than any of them, than the current passing through any of them. If it's been like only one of them. And basically, this is an undesirable thing that we don't want. The deflection in rectifier-based AC ammeter is proportional to the RMS value of the AC current. This is true. Why? Because basically it's dependent on the absolute value of the average of the absolute value, right? If this is the voltage maximum, is proportional to the absolute value, the average of the absolute value. And what we said, that basically RMS is related to, it has a constant, basically is like 0.707 V maximum, okay? And the average, the basically the average of the voltage itself is going to be like 0.69 something. I don't remember the factor, but actually it's another factor times Vm. So basically, if it's a constant times Vm for both of them, then they are going to be proportional to RMS value. Again, the AC ammeter is proportional to, is actually what the actual deflection is proportional to the absolute value of V of t, okay? And the average of the absolute value is going to be like a constant times V maximum. And the RMS itself is a constant times the same V maximum. So basically, they are proportional to each other. If you go to the lecture, you will find that the formula for the average of the absolute value and the RMS value, they are going to be like basic constant times V maximum for each one of them. So if you get one of them, actually the other one will be proportional to it. I didn't say it's equal to, it's proportional to. So the key word here is proportional. Wheatstone bridge is a null method used to measure resistance. So this is very clear. This should be straightforward. A wattmeter can be designed using a rectifier-based AC ammeter. Actually, we didn't see that. We saw a design for the wattmeter using a dynamometer device. We did not see a design for the wattmeter that was based on a rectifier-based AC ammeter. So basically, this is incorrect. The last one here, the changes in the voltage per centimeter scale. So basically, the scale that has basically the one that we saw, basically that you move, the one that you move basically to control the scale on the oscilloscope. What I'm telling you that the changes here, what I change whenever I change that, this is applied by the input attenuator block. Actually, usually it's an amplifier basically. The input attenuator block is usually what's in the probe itself. Okay, the probe has the input attenuator. Okay, the amplifier that amplifies the input voltage basically is what makes this particular part work. So basically this controls the amplification, not the input attenuator block. Okay, so this is false. Okay, so what I'm going to do is I'm going to take that that solution, and basically I'm going to post it for all of you to basically look at, and if you have any question, please let me know. Okay? Do you have any questions now about any of the problems? Yes.
If we want to see our answers for the true and false, I couldn't find it on the grading page.
You will see it now. It actually becomes available after I post the grades. So it should be available. Okay.
But I like enter the exam again, or just from the grade?
Yes, enter. Basically, you go to the grade center and basically click on the exam itself, and basically you will see your answers. You see everything. Did you get your solution? You get your
I just checked
graded. Actually, it's in the same place. Actually, wherever you got your graded solution, you will find the answers to the true/false questions. If you couldn't find it, just let me know. I'll go and try it myself, as I have a student view that I can test the interface with and make sure that it's available.
I just tried it like 2 minutes ago, and there is no.
I'll try it again and make sure I'll try it right after we finish. Okay.
Okay.
Any other questions?
Doctor, I have a question about homework 6. So,
yes, go ahead.
Question number 2.
Okay.
I just didn't understand it. What it was.
Here. This one.
No, in homework 6. Homework 6.
Okay, I'll bring it. That.
Yes.
Okay, here you're going to deal with this as basically just a resistance that was basically you're passing a current through this resistance for a while, so the temperature will increase because of the heat generated from the resistor, and as a result, the resistance itself will be basically will be a little bit larger, so the current will be a little bit less. So let's go and try to solve that. And we went through that before, but let's go through that again. Let me, okay. So basically, what you have here is you have 440 supply voltage, and the temperature was 17 degrees. The current was 2.3 amperes. So the initial resistance will be what? 440 over 2.3. This is R at 17. Okay? Any problems with that?
No.
So after a while, at a different temperature, the current became 1.9 amperes, meaning that the new resistance is over 1.9. So you have here your new resistance here. And you have temperature coefficient, and you're asked to get the temperature here. As we said before, we have a direct law that allows us to do that. R theta over R17 is equal to 1 plus alpha times theta over 1 plus alpha times 17, because actually this alpha 0, meaning that you have here theta minus 0 and 17 minus 0, okay? You have alpha, you have R theta, you have R17, you just get theta from here. Okay. One other question that I was asked about regarding this homework is some people had difficulty reading the colors. Okay. If you look at the colors here, sometimes it's very difficult to know exactly which color is which. Okay. So for example, what is this color? Okay. What is this color? Can you tell me what this color is?
Orange.
It can be orange actually, but sometimes some people think about it as probably brown, something like that. But actually this looks like brown, but sometimes it's difficult to know exactly which color is which. So basically in this part, whenever you're trying to read the colors, just put the colors that you have, put the colors as you saw them on the screen, and compute the result based on the colors that you saw. Okay, and that's it. Don't worry about it. Okay, I'm not going to tell you, no, you saw this as orange. It wasn't orange. It was like a red or something like that. No, it's not going to be like this. Okay, and basically, if I give you a problem like this in the exam, I'm going to read the colors for you. I'm going to put the colors right, basically, for each one of them. I'm going to include the colors for each one of these bands so that you don't have any problems reading them. Okay, so here, just state that you read this as orange, red, green, black, brown, blue, okay, for example, okay? And based on that, the value of the resistance will be this and that, and the tolerance would be this and that, the temperature coefficient would be this and that, and that's it. Would that be a problem? Do you have any problems with that? For the other ones here, you don't have any problems to start with. It's fine. Basically, you have the numbers right away. So you don't have anything to worry about in problems like this, basically the surface mounted components. Any questions? Okay. Should we continue with the lecture? Do you have any further questions? Okay. So basically, by the way, regarding the final exams, as you heard probably, we're not going to have finals, at least not in-class finals. So we are waiting for the college council tomorrow to let us know how we're going to have the finals. There are several options that we heard of. a few of them were like giving the students either pass or fail, okay? So instead of giving grades, every student will get just a pass or a fail, and basically if he gets passed, then the grade itself, the GPA of the student will remain exactly the same as before he took that class. So basically it's like pass that is not included in the GPA, okay? I'm not sure if this is you know, if this looks good to you, but actually it doesn't make sense, because basically this will make a student getting 60 exactly the same as another getting 100, okay? But this is one of the options that might be discussed tomorrow. There are other options related to having basically a take-home exam or something like that, but actually the controls for such exams are very difficult. So it's likely to have, it's likely that we'll have another exam on Blackboard, very much like the one we had in the midterm. Would that be a valid option for you?
Yes,
Do
it's
you have
it's
any
better
problems
than
with the midterm?
pass or fail.
Okay.
Doctor,
Yes.
is the final exam everything or just after the oscilloscope?
Not everything. It has to include everything. By definition, the final exam should include all the parts included in the curriculum, in the course itself. But the parts after the midterm will have a higher load than the parts before the midterm.
Okay.
You don't expect them to be equal, okay? But usually, since we had the most important parts before the midterm, it's likely that they will be equal. They are not going to be like, the actual weight actually is for the parts before the midterm to be higher because they are more important. But actually, they are going to be equal or less than the parts after the midterm. By the way, also what I heard also is what we basically were instructed is that the term will end 25th of Shaban. And meaning that by that date, you will have everything done, including the finals, whatever their options is. Whatever we chose for the final, how we do the final exam, we have to be done with it by 25th of Shaban. So we don't have much time, basically. Anyway, probably by Tuesday lecture, I'm going to let you know exactly what they decided so that we arrange with each other how to proceed, okay? One important thing is the delivery of or the submission of your lab reports. I created an assignment where you submit the first 5 experiments that you already did in the lab. I hope by now, Engineer Mutahir already contacted you regarding the last 2 experiments. Have you heard from Engineer Mutahir?
Nothing.
No.
Okay, so what you should do now is just submit the experiments you have, and I'm going to ask him to contact you as soon as possible to let you know what he wants in the last 2. We're going to have a lab exam. This lab exam will be exactly like the exam that we just have in the midterm. It's going to be only multiple choice questions regarding the question that you would ask about the oscilloscope, about the experiments that you already did, some of the settings in the lab, things of that sort. Instead of asking you orally or as an oral exam, you're going to have a multiple choice question on Blackboard that will count towards the final exam of the lab. Okay, this will be determined probably by next week. We'll let you know exactly the date of that exam once you finish the last 2 experiments.
Doctor,
Okay.
I have a question.
Yeah, go ahead.
When we submit the report of the lab, should we all the groups members submit it, or one?
One member, just make sure that one of you submits the report on your behalf. Okay, so if you're three members or 4 members in each group, one of you is enough. Okay, once we get the lab reports, I'm going to ask Engineer Mutahir to put the grades, and I'm going to post them for all the members of each experiment. So if you have a particular group of 4, for example, I'm going to put the same exact grade for all of you. just be sure to review your lab grades, so that if one of you is missing or anything like that, basically we should catch him. Last term, actually, there were one student actually that was missing in one of the reports. His name wasn't written clearly, so basically he didn't get the grades. But actually, after we posted the grades, he noticed that he didn't have a grade like his colleagues, and let us know, and basically we corrected that. So be sure to review all your grades on your grade center, and let us know if you have any discrepancy, if you have any problems. Okay?
Doctor.
Yes.
Should you submit lab 5 only, or all the previous?
You should submit all of them.
Reports.
Okay, because actually this is the only way I can. Basically, I just want to make sure that we have everything, so that I can ask Engineer Mutahir to put a grade for each one of them, so that you know exactly where you are as of now. Okay, if you submit only experiment 5, then how can he post the grades for the other experiments? Okay, the way it is done now, you have each one of the experiment as a question, and you will have a grade out of 100 for each one, each experiment, and you will get a grade based on the performance in the experiment in each one of these experiments. So you'll know that your grade for each one of the experiments, rather than a total for all of them. So that if you have any problem, for example, you can ask him and maybe correct if there is any mistake or something like that. Okay?
Okay.
One final comment before we proceed. About 3 students actually didn't attend the exam. Okay? I'm not sure exactly what their problem might be, but actually they have to contact me right away to correct their or to see what to do. One of them actually didn't even log in to Blackboard since the start of the term. So I'm not sure if he's going to be basically aware of any exams to start with. And maybe I'm sure he didn't attend any of the lectures, because actually, if he attended, he would know that there are assignments and at least the course material he has to download from the Blackboard site. So basically, one of the students actually is very likely to just get a failing grade. But the other one, at least he attended before, okay? But he didn't attend the exam. So basically, if you know one of your colleagues who didn't attend, please ask him to contact me as soon as possible, okay? Okay. Now what I'm going to do is basically try to go over what we talked about last time. We said that if you have an experiment that looks like this, a situation that looks like this, and basically we have a switch here like this, and if we flip the switch to A, and we have a capacitor here that wasn't charged, that has a charge of 0, then we will have a voltage difference across this resistance, and this will pass a current to charge the capacitor, and this current will basically decrease as the time passes, because basically the voltage difference will be less, because the capacitor here will be charging, and the difference between the battery and the voltage on the resistance will basically go to 0 eventually. So the current will basically be exponentially decaying curve, and the voltage on the capacitor will be exponentially growing curve. And what we said last time is that we have a very simple rule for that. If I'm talking about any quantity, for example, V of t, is going to be basically equal to V initial minus V final, e to the minus t over tau, which tau is the time constant, okay? Tau is basically RC, plus V final. If you look at this equation, this will be equal to 0 when for t equals to infinity, and it's going to be equal to 1 when for t equals to 0, right? Just plug in t equals to 0 here. This will be e to the minus 0, which is equal to 1. And if you plug in t equals to infinity, then this will be e to the minus infinity, which is equal to 0. So basically, if it's t equal to 0, then this will be equal to 1. This will be equal to Vi minus Vf plus Vf, which is equal to Vi. V initial. Okay, V final is at infinity. So if you put here t equal to infinity, then this will be equal to 0, and the output will be Vf. This will apply to both the voltage and the current anywhere in a circuit like this. Okay, so let's try an example to apply that. Here you have a situation like the one that we saw. We have an 8 microfarad capacitor. Let's just draw the circuit. You have 8 microfarad capacitor. Okay. Connected in series with a resistance. Okay. And you have a supply of 200 DC supply of 200 volts. Okay, and this is 0.5 mega, and this is 8 microfarads. Okay, this connection was made at t equals to 0, basically. So the capacitor was not charged, so the voltage on the capacitor at 0 is equal to 0. So basically, the capacitor of 0 is equal to 0. Okay, and basically the time constant here will be what? Because you have one capacitor and one resistance, tau, time constant will be equal to RC, equal to what? 0.5 times 10 to the power 6 times 8 times 10 to the power minus 6, which is equal to what? 4? For what? What is the unit here? What is the unit here? Seconds, right. Okay. So now he's asking for the second part. So this is done. The second part is asking for the initial charging current. The initial charging current basically will flow here at t equals to 0. So at t equal to 0, you have a voltage difference across this resistance of 200 minus 0. So the initial current, IR of 0, is going to be 200 minus 0 over the resistance 0.5 times 10 to the power 6, which is going to be equal to what? 400, 10 to the minus 6, which is what? 0.4 milliamperes, right? Right?
Yes.
Okay. The time taken for the potential difference across the capacitor to grow to 160 volts. Now what we have to do is we have to develop the equation, we have to derive the equation for the voltage across the capacitor so that we can answer this question here, So let's apply the rule that we just saw before in the previous lecture, previous slide. So it's going to be V initial. V initial is equal to what? 0. V final is equal to what? What is the final value of the voltage across this capacitor? If we leave this long enough, it's going to be basically the 200 volts will charge the capacitor completely. Basically, the charging current will end when you have 200 volts here and 200 volts here. So the voltage across the capacitor at infinity will be equal to 200 times e to the minus t over 4, which is the time constant we just computed here, plus 200, which is the final voltage, which is equal to 200, 1 minus e to the minus t over 4. What he needs to solve here basically is the time taken for the voltage to grow to 160 volts. So what I'm going to do here is just make this equal to 160 and solve for t. Can we do that? It's very simple. It's a single equation in single unknown. You have everything except for t. Okay? So basically from this you get t 160. Can you do that? Any problems with that? Any problem?
No.
Okay. Here, the part D is asking for the current and the potential difference across the capacitor 4 seconds after it is connected to the supply. So what you're asked for in this part particularly, you need to compute VC of t at t equals to 4. So just substitute here. Basically, maybe I can write it in a different way. What you need to compute is VC of 4. Okay, just substitute t equal to 4 in this equation. It's very simple, direct substitution, you get VC of 4. Once you do that, you can very easily get the current, which is what? I will be equal to 200 minus VC of 4, this is I of 4, over R. Because basically whatever voltage here, whatever voltage you have here, and whatever voltage you have here, basically the difference between the two will be across this 0.5 mega resistance, and it will determine the current. So basically it's going to be 200, which is basically the voltage of the battery or the voltage source, minus VC of 4, the voltage on the capacitor at time t equals to 4 seconds over R. And you can compute that as well. Do you have any problems in solving this kind of equations or this kind of problems? This is like a circuits problem, really. It's not really, doesn't have anything new, actually. You should have solved things like that, like in maybe 250 or maybe 301 at least.
301, yes.
Yes. Do you have any questions about this problem? Okay. So basically, this kind of problem actually is very similar. If you understand how to work with this equation that we just talked about, you can solve any of these problems without any difficulty. Okay. There's another problem here. It's a little bit different, but actually it's very similar. It's not that much different. What you have here is a circuit where at t equal to 0, you get that that switch actually is switched to position 1, okay? And basically at t equals to 100 milliseconds, you flip it to switch 2, to the switch position 2. So basically it remains from 0 to 100 milliseconds in position 1. And then it switched to position 2. Basically, if you look at this circuit, the capacitor is initially uncharged. So when you flip it to position 1 here, what's going to happen is that the capacitor here will start charging. Okay? So basically, it's going to charge through the resistance here from the 10-volt source. So you have a time constant that is equal to this R1, which is 100 kilo ohms, times C, which is 0.1 microfarads. At 100 milliseconds, the capacitor is partially charged. It's not going to completely charge to 10 volts, of course. Okay? It's going to be partially charged. It's going to have a certain charge here. Okay? When you switch to position 2, this charge will be connected across a resistance of 200 kilo ohms. So what's going to happen here is that the charge here will flow a current through the resistance here and discharge the capacitor. So basically, you will have another problem where you have only a capacitor and another resistance in series and basically solve for this problem. Let's try to solve the first problem first of all. Let's start with the switch at position 1. Okay, so at position 1, okay, you will have RC equal to what? 100K times 0.1 micro is going to be what? It's going to be 10 times 10 to the minus 3, right? Okay. Seconds.
Minus.
You'll have 10, basically 0.1 times this is going to be 10, and K a microfarad, this is 10 to the power 3, 10 to the minus 6, and it's going to be 10 to the minus 3, right?
Yes.
Okay. So what you're going to have is like 10 milliseconds. VC in the first circuit, in the first position, will be equal to, as a function of t, is going to be equal to 0 minus the eventual, if I leave it for till infinity here, is going to be 10 e to the minus t over tau 1. Let's just call that tau 1, okay, plus 10, which is equal to 10, 1 minus e to the minus t over tau 1, okay? At 100 milliseconds, you can compute that here. You can imagine that basically t here is going to be 100 milliseconds, and this is tau. Tau is equal to 10 milliseconds. This is 10 times this. If you actually allow 10 time constants to pass, this will be close to having VC here equals, it's going to be approximately equal to 10 volts, approximately, okay? Whatever, basically, if you want to get the exact value, just substitute here with t equal to 100 milliseconds and get the exact VC at the point where the switching happens. Once the switching happens, what you're going to have is another circuit where basically the circuit will be basically just these two resistors, the capacitor with just one resistor, R2, and VC in this case, VC dash, okay, will be equal to, the initial voltage will be basically what you have here, what you have from this value here. If it's 10 volts, let's just assume that it's V100, okay? Let's just call this V100, okay? So the initial value will be V100 minus 0, because eventually if you leave this circuit running forever, the capacitor will be completely discharged, times e to the minus t over tau 2 plus final value 0. So basically it's going to just be like this. What he's asking for here is that you should determine the expression for the capacitor voltage and current. Basically this will be the expression for the voltage, and the current will be what? IC of t will be equal to what? Exactly VC of t over R2, because whatever voltage is across this resistance is going to be exactly the same. Here it's going to be exactly the same, by the way. IC of t is going to be exactly the same, VC of t over R. Oh, so here actually, I'm sorry, it's going to be like 10 volts minus VC of t over R1. The point is here, in the first circuit, the current will be flowing like this. In the second circuit, the current will be actually flowing the other way, because actually the voltage will be here positive and here negative. So the current will be actually flowing in the opposite direction. So whatever the sign for this current is going to be opposite to the sign of this current. But you can still compute everything you want here. Okay. He wants you to plot the voltage and the current waveform from t equals to 0 to t equals to 200 milliseconds. Basically, let's try to draw both of them here. Just assume that this is 100 and this is 200. Okay. The capacitor voltage, assuming this is 10, okay, is going to be very likely to be like this until it reaches here, almost at 10. And then it's going to decay exponentially like this here. This is for the voltage, VC of t. For the current, if we assume the current direction in this way, basically is going down like this. So basically it's going to start very high, because actually at the beginning, the highest voltage difference will be at the beginning, where the potential difference across R1 is equal to 10 minus 0. So it's going to start like this and decay until it becomes almost 0 at 100. And then after you switch, okay, the current will be actually highest as well, but actually it's going to start from a negative value and decay like this. till it reaches 200. It's going to be a negative value. So it's going to start instead of being here at a positive value, because actually the current in the second circuit will flow in the opposite direction. You're going to see it like this. Let me draw it here just to make sure that it's clear. Okay, so the current in the other direction here, the current in this circuit here will flow like this. Okay, here is going to flow like this. So basically the current here, this is here going like this, and this is here going like this. So basically they are in opposite directions. So if you take the convention for IC of t as positive here in the first part, the first 100 milliseconds, you have to make it negative in the second 100 milliseconds. Okay, so after the switch, this is where the switching happens. This is switch 1, and this is switch 2 happen. From 1 to 2, it's going to be positive, and from 2 afterwards, it's going to be negative. That clear? You have any questions? Okay. So next time, inshallah, we're going to start talking about the energy storage in the oscilloscope, in the capacitor. And basically, we're going to talk about some of the interesting parts that probably you haven't heard of much before, like the leakage across the capacitor, basically the effect of having different dielectric materials and how they affect the leakage that happens in the capacitors. We're going to talk about the forces applied to the deflection, to the capacitor plates, and because actually this can affect also the performance of the capacitor and things of that sort. And basically we end up with an application that we talked about before. We're going to go over again just to emphasize it and basically discuss some of the other applications for capacitors. Okay, so I expect inshallah that on Tuesday we're going to finish the capacitors based on that. Okay, for the inductance part, let me tell you what we have left in the class. The inductor part, I thought about increasing the part of the inductance like I did with the capacitance and the resistance, but I thought we have a very tight time schedule, and I'm not sure exactly how you are doing in the other classes. So basically, I'm going to give it the way it is. It's going to be just one lecture to finish the inductance. It's going to be very simple. We're not going to go into much details in the nonlinearities of the inductances. So it's going to be really simple. And after that, we're going to have about a couple of lectures talking about the sensors. So I expect that we are going to finish everything by the end of next week, inshallah. Not this week, next week, inshallah. Okay? After that, we're going to meet for lectures, but actually all the lectures will be just review lectures. Okay? If you want me to explain anything again, from the start of the class till now, till the end of the whatever we're going to cover, I'm going to go over it again. I'm going to explain it again. If you want to go over questions or problems or anything like that, I'll be happy to do that for the rest of the term, inshallah. Okay? But hopefully before then, we're going to determine what we are going to do about the finals so that we can schedule it early on rather than having all your finals crammed in 1 week. Because actually the current plan is that you're going to have almost all your finals in 1 week. Okay? So basically, we're going to try to, at least in this course, we're going to finish early so that if you want to have a final exam before then, before the finals week, the actual finals week, we can do that. Okay? So please try to let me know if you have any problems with any of the new parts. And if you have any problem with the old part, please wait until we finish the planned parts of this course. And basically, you're going to start reviewing them again. Okay?
Okay.
Okay. So I'll see you, inshallah, on Tuesday at 1, inshallah. If you have any questions, please feel free to stay and ask me. Okay? Any questions?
Sure.
Yes.
The homework 6.
Yes.
The first question, I'm not sure what I should do with the number of turns and the cross-section area.
Okay. Here, basically, what you need to have here is the length, the total length of the wire, right? He's telling you that basically the wire itself has a cross-sectional area of 0.8. This is a cross-sectional area of the wire, not the cross-sectional area of the coil, okay? Basically saying wire having a cross-sectional area. So basically this is the A that you want, okay? The resistance, as we saw, is rho L over A. You have rho, you know, basically this is the resistivity. You get it from the, you basically, it's given here as 0.2, 0.02. It's given here, okay? You need to have the area and you need to get the length. The length here is given as it's 80 centimeters per turn, meaning that each one of these 2,000 turns has a length of 80 centimeters. So the total length would be what? 2,000 times 0.8, so that you get it in meters. Okay, that's it. So you have rho L over A, you have all the parameters you need to compute your resistance. After that, he's asking for the power dissipated in that resistor, okay? When you connect it to a voltage of 100 volts, 110 volts. Once you computed the resistance, the power is gonna be V squared over R. That's it. Any questions? Any other questions?
Thank you, Doctor.
Sure. Okay, if there aren't any more questions, we'll meet on Tuesday, inshallah. I will post the solution for the midterm exam, and please let me know if you have any concerns regarding your grade, okay? By the way, the grades that are posted are without any bonus, basically. They are the actual grades. I usually fit the grades to a curve. So you would expect your grades to be a little bit higher, okay? My expectation is that each one of these is probably gonna get like 10 points plus the original grade. So if you're getting like 80, you're gonna be like 90, okay?
Doctor?
Basically, each one of you will get like 10 more points when I fit the curve, okay, of the grades. What you have, the grades that I gave you are the actual grades, okay? By the end of the term, I increase the grade a little bit. So basically, my expectation is that for this particular midterm, you're gonna get 10 more points for, on top of what you already have. So if you get like 80, you're gonna be 90. You get like 60, you're gonna be 70, okay?
Doctor?
Yes.
There was in a previous lecture you mentioned something about a bonus question, but there is nowhere to like submit it. Like
actually, I'm worried. I was worried first of all about the exam. You didn't have much time before the exam. I'm gonna do that. I'm gonna post that particular bonus question, but I don't think you will have much time to worry about bonus questions. With the other subjects and the hurry to finish everything. So basically, I'm going to post that particular bonus question, but I'm not going to post any more. But you will expect that I will actually give you bonus points, anyway, without any bonus questions, because actually I'm concerned about the effect of what happened in the term on all of you. So basically, I will make sure that each of you will get enough points to basically get to the next grade. Okay, so but whatever you're getting, whatever your current grades are getting you, you're probably gonna get to the next grades from that particular point. So if your total grade is like P, you expect to get like P plus without doing anything further. Okay, so basically this was the function of the bonus points or the bonus assignments. I don't want you to worry about the bonus assignments. I want you to worry about the actual content, to study the actual content. I don't want to distract you with bonus questions, but I'm going to post that particular bonus question because I told you that I will. Okay, but I'm not going to post any further bonus questions. Okay?
Thank you.
Okay, good luck, inshallah. Okay, thank you. I'll see you next lecture, inshallah.